Hi, today my group will presenting our topic titled Electromagnetic Wave Generated by Earthquake. This is my group members, Siti Nur Rusdina, Nadira and me, Tan Suhui. Today we will share about what is wave, what is an electromagnetic wave, and how this electromagnetic wave can be generated by earthquakes. Let's begin with the basic question, what is wave? A wave is a disturbance that transfers energy from one place to another without moving matter. This means that when a wave passes through something like water or air, the particles don't travel with it, they only vibrate. There are two main types of wave. The first one is mechanical wave, which need a medium like sound or water wave. The second one is electromagnetic wave, which can travel even through space. Now let's move on to electromagnetic wave. Electromagnetic waves are a form of energy that travels through space as coupled oscillating electric and magnetic field. They can travel through air, solid object, or even vacuum, meaning they don't need any medium. They move at the speed of light, and examples include radio wave, microwave, infrared, visible light, ultraviolet, X-ray, and gamma rays. All these waveforms we can call the electromagnetic spectrum. These waves are very important in our daily life, such as in communication, medicine, and satellite system. For example, we use synthetic aperture radar in earthquake and land movement study. This picture shows how electromagnetic or seismic waves spread out from the earthquake focus underground and how scientists detect them using sensors. The red circle at the bottom marks the focus, which is the point where the earthquake actually starts. The red arrows show how the energy waves spread out from the focus through the ground. Around the surface, there are sensors labeled sensor 1 to sensor 6. This device detects the vibration or electromagnetic signals produced by the earthquake. The small graph beside each sensor shows wave recording. You can see that the signal looks stronger when they are closer to the epicenter and weaker when they are farther away.
Hi everyone, my name is Siti Nurushdina. I'm going to talk about how electromagnetic wave or EM wave are using in geoscience, which is basically the study of the earth. So, EM wave ini sangat penting sebab dia boleh membawa tenaga tanpa perlu medium. Maksudnya, ia boleh travel dalam vacuum, contohnya dari matahari ke bumi. Dalam bidang geoscience, EM wave ini sangat penting untuk bagi kita mengkaji permukaan bumi, lapisan bawah tanah dan juga atmosfera. They help scientists explore, monitor and understand our planet better. Let's start with physical concept. EM waves have three main properties: speed, wavelength, and frequency. This determine how the wave behave and what they can be used for. Contohnya, gelombang radio digunakan untuk komunikasi, infrared untuk mengesan haba, dan contoh tampak untuk ambil gambar bumi dari satelit. Setiap bahan atas bumi, macam tanah atau batu, akan pantulkan dan serap gelombang EM dengan cara berbeza. That's why scientists can identify material just for look at the spectral signature. Next, let's talk about remote sensing. This technique that use visible and infrared radiation to study the Earth for satellites or aircraft. Melalui keadaan ini, kita boleh kaji guna tanah dan pertanian, lihat keadaan hutan dan pantau kualiti air serta suhu permukaan bumi. In short, remote sensing helps us see the Earth without even touching it. For geophysical exploration, this part focuses on using EM wave to detect what beneath the ground. Contohnya, electromagnet inclusion boleh detect logam, air bawah tanah atau minyak. Ground penetrating radar ataupun disingkatkan GPR boleh digunakan gelombang mikro untuk tengok lapisan bawah tanah atau runtuhan lama. Dan teknik magnetotelluric method digunakan untuk kaji struktur kerak bumi dan magma di bawah permukaan. So basically, EM wave ini bantu geoscientists see things we can see without our eyes.
Alright, so I will start by introducing the main subtopic for our presentation. This part we are looking at how electromagnetic waves are applied in environmental studies. Specifically, we are focusing on how electromagnetic waves are used to measure atmospheric gases and temperature. This is an important method in Earth observation, especially when studying climate change. The idea here is that different gases in the atmosphere observe and emit electromagnetic radiation at specific wavelengths. By analyzing these wavelengths using satellite or ground-based sensor, scientists can monitor change in temperature, greenhouse gases, and other atmospheric conditions. So this is one of the ways the principle of physics are applied directly to environmental science, and later we will connect how these same electromagnetic principles are also involved when studying earthquakes. Before we discuss how earthquakes generate electromagnetic waves, it is important to understand that any data we observe from satellite can be influenced by several external factors. This diagram shows the sources of error or noise that we need to filter out before we can correctly identify electromagnetic signals that are related to earthquake. First, we have atmospheric effects. Cloud, haze, and aerosol can scatter or absorb electromagnetic radiation. This may cause the satellite to misinterpret surface signal, especially in cloudy or humid regions. Next, we have sensor calibration and degradation. Satellite instruments age over time and different satellites may measure slightly differently. So, when we compare before and after quick data, we must ensure the sensor data is calibrated correctly. We also need to consider ice, snow, and topography impacts, especially in mountainous or polar regions. The surface reflects radiation very strongly and can create false anomalies that look similar to electromagnetic change caused by seismic activity. Another major factor is the BRDF effect, which means the reflectance depends on the geometry between the sun, the Earth's surface, and the sensor. So the time of day and satellite angle can influence the signal we receive. Soil conditions also play a role. Moist or dark soil reflects radiation differently compared to dry or bright soil. This means change in soil moisture can sometimes mimic the electromagnetic anomalies that occur before an earthquake. Finally, we have data processing artifacts such as atmospheric correction, filtering, or image compositing. If these steps are not done carefully, they can introduce artificial patterns into the data. So the key takeaway is, before we can confidently say that a signal is caused by an earthquake, we must first remove all of these external influences. Only after this correction are made can we detect real electromagnetic anomalies that may be linked to seismic activity. Now that we have an overview of this general idea, I will move into the subtopic of our presentation and how they related to the depth of understanding required for this subject. For this topic, we are focusing on how energy transfer principles from physics are applied in Earth observation, particularly when detecting electromagnetic signals occasioned by earthquake. In other words, we are not just looking at the phenomenon itself, but also how we observe it, how the energy is transmitted through the atmosphere, and how satellites interpret the signals. This helps us understand the process from the ground where the earthquake stress occurs all the way up to the ionosphere where the electromagnetic wave can be detected. So in the next part, I will break this down into smaller subtopics to explain each stage clearly. This slide shows how different parts of the electromagnetic spectrum interact with the Earth's atmosphere. Not all electromagnetic waves can reach the Earth's surface or be detected from the ground instruments because the atmosphere absorbs certain wavelengths. On the left side, we see that gamma rays, X-rays, and most ultraviolet lights are blocked by the upper atmospheres. This wavelength can only be observed directly from space-based satellites. In the center, we have the visible spectrum, which is the part of the electromagnetic spectrum that reaches the ground most effectively. This is why our eyes evolved to see this range. Next, much of infrared spectrum is observed by atmospheric gases like carbon dioxide and water vapor. So to measure infrared radiation accurately, we usually rely on satellites above the atmosphere. On the right side, we have radio wave. Many radio wavelengths can pass through the atmosphere, which is why radio telescopes on Earth can be detected. However, very long wavelength radio waves are blocked. This is important for our topic because some of the electromagnetic signals generated by the earthquakes occur in the radio and infrared range. So we need to choose the appropriate method, either ground observation or satellite observation, depending on which part of the spectrum the signal appear in. In short, understanding which wavelength can pass through the atmosphere helps us to decide how and where to detect electromagnetic anomalies related to the earthquakes. So now we'll look at the main problem that researchers face when studying electromagnetic waves generated by earthquakes. Earthquakes can produce electromagnetic signals because of stress in rocks, cracking of the crust, or the movement of underground fluids. These signals may occur before, during, or after an earthquake. So there is a possibility that they could be used as early warning indicator. However, the challenge is that these electromagnetic signals are usually very weak and they are often mixed with noise from human activities like communication system, power lines, or even natural sources such as lightning or solar radiation. Because of this, it becomes difficult to confirm whether a detected signal is actually related to seismic activity or just background interference. To solve this, scientists use instruments like magnetometers and electric field sensors to continuously record data. The recorded signals are then analyzed to check if the pattern match known earthquake-related electromagnetic behavior. So the main difficulty here is separating real earthquake signal from noise. Only if we can reliably isolate this signal, then electromagnetic wave can help us understand earthquake better or possibly provide early warning before an event occurs.